All right, so presumably you all are here for radiobiology, yeah? Good. So what we're concerned with is the interaction between radiation and living systems. More specifically, what I'm going to speak to is ionizing radiation, and I think that's probably what you'll be dealing with the entire semester. This is a nice little diagram that I'd like to begin with. If you were standing on a football field and you were to drop a little BB at midfield, right, that would represent the size of an atomic nucleus, and the entire field would then be the size of the atom, right, the electron cloud, et cetera, et cetera. So what it's designed to convey is that the nucleus is very, very tiny, and in comparison, the atom is sort of big, the electron cloud. That aspect, that part of the atom is large, the nucleus is really, really small. Neutron and proton masses are about 1,800 times the mass of the electron. It gets a little goofy. For me, it's difficult to talk about volumes when you're speaking about particles of this size, but while the electron is much less massive than protons and neutrons, it's actually larger. The cross-sectional area, we'll say, is much larger than the proton and the neutron. So again, this is to illustrate that the nucleons themselves are really tiny and very massive. Units, it gets out of hand quickly if you want to use like MKS units, right? So typically you'll use different units rather than meters, kilograms, seconds, joules, things like that. So you'll come up with different units that are more appropriate to the energies, to the sizes, to the masses of the particles that you're discussing, right? So atomic mass units are typically used. There are other units that you can use as well. This one is just common. So Einstein, right? Mass and energy are equivalent. E equals mc squared. I don't know if you guys have followed any of the news that they've been releasing lately from CERN that talks about neutron speeds, and these massive particles are exceeding the speed of light, which is energetically not possible. I think there's a problem with the measurement of the time. We'll see. But there is and has been sort of a disagreement or some sort of conflict about whether or not these neutrinos can actually fly faster than the speed of light. Any massive particle, according to Einstein, cannot exceed the speed of light. So these are just the masses of the proton, the neutron, and the electron, and that we talked about. All right, so electron volts, this is a unit of energy that is commonly used when discussing these types of particles. All right, so you take an electron, you drop it into an electric field that's got, I don't think very quickly early in the morning, sorry about this. 1 volt of potential difference across 1 meter, right? So the energy that it acquires as it moves through that 1 meter, through that potential of 1 volt, right, is an electron volt of energy. And then there are multiples of those, keV, meV, geV, etc. Charges, right? So when dealing with currents in the macro world, it makes sense to talk about amps and coulombs. When you're dealing with smaller particles that conspire to make up currents, they're much, much smaller, right? So we can get down, it's just a specific unit. An electron will have a unit of negative charge. A proton will have a unit of positive charge, right? So in order to get a coulomb of this stuff, right, you have to have a large collection of either protons or electrons. The Bohr model. There are different ways to describe the electrons in the different shells about different nuclei. This kind of notation, the K shell, the L shell, the M shell, etc. That's one way to do it. It's commonly used. I prefer spectroscopic notations, S, P, D, F, but all that you're doing is describing the electrons that are occupying the different orbitals around the different atoms, right? So It's common. You should be able to recognize both of them. For our purposes here, the only one that's really going to matter is n, which is the principal quantum number, and that describes the different orbital, right? So 1n1, right, would be the first electron in the first shell, right? So the K shell is typically what we're going to be confining our remarks to today. All right, so the diagram shows a characteristic X-ray. If you have a vacancy in the K shell, an electron in the L shell, as it drops from L to K, right, there will be an emission, a photon, and it will carry a specific and discrete amount of energy. You can measure this stuff, right? The idea here is that there are discrete energy differences between the shells. So as an electron moves from one to another, right, you should be able to measure this and identify it. Spectroscopy is done in this way. You can identify unknown radionuclides or isotopes, right, simply by the energy that's emitted. Binding energy. This is kind of quirky and it takes a little getting used to. Most of the time, right, when they're discussing electron energies, right, they'll consider an electron that has moved out to some distance free of its nucleus. We'll define that as a zero energy. And as it falls in toward the nucleus and gets more tightly and tightly bound, it's considered to be a negative energy. This is something that I doubt you'll deal with, right? So you could define it as being zero where it's most tightly bound, but it's commonly not done that way. It's just notationally different. Right, so as Z increases, the number of protons in the nucleus increases. The likelihood that an electron is going to be more tightly bound increases as well, right? So it's just a talk about the energy. Most of what you're going to deal with has to do with ionization. There are some processes whereby as a photon interacts with an electron, it will move to a higher orbit, it will become excited. Matter doesn't like to be in an excited state, so it seeks to be as energetically stable as it can be. So typically it will emit a photon and drop down to this lower energy level, right? So that's excitation. Ionization just refers to ping, knocking something, an electron, off of the atom. All right, so what you're going to deal with is damage from ionizing radiation, right? And as you remove electrons from biological molecules, they can become distorted, they can become damaged, they can essentially be killed, right? So if you have a large cell, right, that contains a great number of atoms and molecules, disrupting the function, the way that these molecules are bound together can result in damage to the cells, to the system. All right, so briefly we'll run through radioactivity here quickly. Atoms prefer, right, that there's a roughly equivalent number of protons and neutrons when the atomic number is small, right? As the atomic number increases, right, you need to include a larger proportion of neutrons, right? And we'll get to this shortly. The reason is because of Coulombic effects in the nucleus, right? If you have a bunch of protons with similar charge that are really close to one another, there is a strong force that holds them together, like a spring, a latch, right? But if you get a high concentration of these protons, the distances between them, right, can bring the Coulombic interactions into play and can disrupt the strong force and disrupt the nucleus, right? So as you get to increasing masses, the number of neutrons in the nucleus should increase so that the atom is stable. Right, and so this is the line of stability. It'll become clearer as we go along. Right, so in the nucleus, the neutrons have no charge, the protons have a positive charge of 1. Right, so the Coulomb force between them, this is what we were talking about, it can become overwhelmed. It can distort the shape of the nucleus. It can cause decay. But again, if it's spread out properly and if there are a number of neutrons to help latch onto the protons and neutrons in the nucleus, right, it improves the chances that the atom will be stable. The strong nuclear force only operates over very short distances, about 10 to the minus 15th meters, very, very tiny, very, very short, right? So if you have 2 protons that are at distances that are larger than that, the strong force will not work whatsoever. I mean, it only operates over a very, very short distance. I think we've killed that. Okay. Well, so in decay, if you have an original nucleus that's undergoing some sort of decay, that's typically referred to as the parent, right? The product, the resultant atom is referred to as the daughter. Okay? In radioactivity, right, 1 disintegration per second is called a becquerel, and there are different units that are used for this as well. The Curie is the one that I like to use because I'm old. It makes sense to me. This is how I think. Right? So different people will use different units. You can convert them. It's simple. Right, so as these atoms undergo decay, there is some sort of emission. Sometimes it's a particle. Sometimes it's a photon. It doesn't really matter. You can understand, we do understand what is emitted from radiations of different types. Again, you can do spectroscopy on alpha emitters. On beta emitters, it's not quite as simple. On gamma emitters, it's pretty straightforward, right? So these energies are known, and you can measure them, and you can identify the different isotopes that are emitting these radiations, right? So nice little electromagnetic spectrum. This stuff is known to you, right? Some of it you know better than others, right? So very low frequency, long wavelength, low energy photons, electromagnetic radiation, right? That's radio waves at one end, right? So as you increase in energy, increase in frequency, a shorter wavelength, right? As that increases, right, that you move through the spectrum, right? So visible light, this is something that we're all acquainted with. What we're mostly interested in today and in this course is the very energetic stuff, the X-rays and gamma rays. Right, so this is just a diagram of a wavelength of a wave. Frequency and wavelength are related, right, for radiation, for light. The product of the frequency and the wavelength is always equal to c, right, the speed of light. If you're dealing with sound waves, if you're dealing with waves on the ocean, the product of the frequency and the wavelength will always be the speed at which this wave is propagated. Right, so for light, it's straightforward. In a vacuum, the speed of light is 3 times 10 to the 8th meters per second, right? You can then do calculations knowing one or the other, frequency or wavelength or energy, right? You can then discern the other qualities. It's a simple algebra, pretty straightforward. Let's see, photons are massless and chargeless. The neutrinos that we were speaking about earlier, I have a bias there. They're magic little particles. They're weakly interacting. But photons, these are things that you can measure. They're things that we know about. Right? The photon energy, right, you can calculate or measure, right? And Planck's constant is fundamental to the universe. Matter, I get out of my depth here pretty quick. If you're trying to describe the energy, the motion of a charged particle, an electron, for example. Planck's constant is fundamental to understanding its energy and its motion. Okay? It comes up everywhere, right? So when calculating the energy of a photon, you can either use the wavelength or the frequency in the calculation. But this Planck's constant is just a constant, right? It's a simple multiplicative constant that you use to calculate the energy. And this is the relationship. Right? So ionizing radiation, that's what we're interested in. What knocks electrons off of atoms? Right, so these are the different processes that I'll go through pretty quickly. Presumably, again, you guys are smart and have been through this stuff and are familiar with them, so we'll rush to them. Alpha decay, it typically occurs only in the heavier elements. What it does is it spits out a helium nucleus. Right, so that's 2 protons, 2 neutrons. There are no electrons associated with it, and it's typically very energetic, usually between 4 and 6 MeV. This is a nice little diagram of it. It's radium-226 going to radon-222. Right? So again, all it's doing is spitting out this helium nucleus, right? And it's seeking to become more energetically stable. Right? The good and bad thing about alpha particles, they're very energetic, but they don't travel very far. They're easily stopped. Right? The dead layer of skin, a piece of paper, these things are typically adequate to stop an alpha particle. It's because they interact quickly and they lose their energy through a series of collisions, but the range of these particles is not that great, right? So as long as they stay outside of your body, there isn't much of a hazard. Once they get inside your body, they can raise all kinds of hell, right? And so this is a nice little electron micrograph of plutonium in the lung and the action of the alpha particle emission on the lung tissue. So again, the trick is to keep it outside your body. Most of these things too, alpha emitters are bone seekers, so they will go to the bone, and as they decay, they can cause problems. Radon is the one with which you are probably most familiar. It's part of the uranium decay series. You breathe this stuff in, it decays in a quick series of decays through several isotopes, and that's why people make such a big to-do about radon in the homes. Beta decay. This is a guess, but I would say most of the isotopes that we deal with and that you've heard of will decay by beta emission. Right? And all that happens here is that the nucleus will spit out an electron, right? And it's changing its identity when it does this. It changes the number of protons in the nucleus, right? And it's just an ordinary electron, and energetically it's a little more strange because in beta decay, right, there is also an antineutrino that is carried off. That will carry off some of the energy. It's unknown beforehand how much it will be, right? So the beta particle, the electron, will carry some fraction of the energy available, and the antineutrino typically will carry the rest. There is, of course, conservation of charge and momentum. Right, so it gets a little ticklish, but the maximum energy from any isotope that a beta particle may carry off is known. Right? And we'll talk more about that briefly shortly. So what's going on here is P32, phosphorus, decays by beta emission. It goes to sulfur, right, spits out an electron and an antineutrino. And I've already told you that I'm skeptical about the neutrinos being massless. So this is a look at the typical beta energy spectrum. The average energy of a beta particle emission is about 1/3 of the maximum energy available. All right. Why that is, I don't really know. I just know that that's the case. You just have to take some things on faith. This is one of them. You can measure it. You can prove it. Why it occurs in that fashion is beyond me. I don't know. It just happens that way. Tritium is probably the one beta emitter that we'll use on campus that has a very low energy comparatively. It's about 18 keV. You can get some beta emitters that are very energetic. The range of the beta particle, the electron, in tissue, in water, in air, that's going to vary by energy. The example that I give here is that an electron can travel about a half a centimeter per MeV, right? Because of the way it loses its energy, because of the way it interacts with other matter, plexiglass is typically used for shielding of these materials. Lead isn't the best choice because of Bremsstrahlung interactions that we'll talk about shortly, and this too is something that should be known to you. I mean, that's how we produce X-rays for diagnostic stuff or therapeutic stuff. Positron emitters. The one that we're most familiar with is F18, right? So it's similar to beta decay. It's an electron, the antiparticle of the electron. Okay, so its charge is positive rather than negative, but in all other ways, it's just like an electron. So I think the arrow on this one goes the wrong way, right? So F18 goes to oxygen 18, right? It emits a positron, spits out a neutrino, and the way that they produce this stuff, they'll have an oxygen target and then bang protons into it, right? So it's just the inverse of this transition. It's useful in the clinic. Many of you are probably familiar with it. There are many positron emitters that we can produce, but they don't linger for long, very short half-lives. The problem is, once the positron is emitted from the nucleus, right, it will find a normal electron to interact with. These two will interact and they will annihilate one another very quickly, right? So commonly, there are two photons that are a result of this interaction, right? And they go in different directions, and they're at least 511 keV, right? So it's energetically, it's a very energetic interaction. It's useful, but antimatter doesn't stick around very long in our part of the universe. Electron capture. What happens here is there are too many protons in the nucleus, right? And essentially the nucleus will reach out and snatch an electron. So one of these protons is converted to a neutron, right? And it leaves a hole typically in the K shell, right? So the proton is converted to a neutron, an electron is then missing from the K shell, so the electrons in outer orbitals will then fall down into lower levels, and there will be characteristic X-rays that are emitted, right, in these transitions. That's not a very good example. Does this look like electron capture to you? Because it doesn't to me. A good example is I-125. This is just a bad diagram. I'm sorry about that. I-125 would be a better example. There are many such examples. Commonly, the photon energies from electron capture are going to be comparatively smaller. And I should make a note of that. It doesn't occur that frequently. Some isotopes will use it, but not that many. Many times, particularly after alpha decay, the alpha particle will be spat out from the nucleus, and the nucleus is still shaking, rattling, spinning too energetically. We say that it's in an excited state. So this gamma ray emission, right, can accompany beta emission, can accompany alpha emission. There is almost always some sort of photon emission that's accompanying alpha decay. Right? We've got a nice little diagram of this. Cobalt-60, this is something that we use for calibration. It's pretty energetic. It spits out a couple of photons, but the gamma rays that are emitted are actually emitted from the nickel-60 that's in an excited state. So the diagram here says that cobalt-60 spits out the beta particle, nickel-60 is in an excited state, and then in order to go down to the ground state, it spits out this photon. These things happen pretty quickly, fractions of a second, right? So it's just a nice little diagram for that. The gamma ray energies are known, you can measure them. The thing to remember here is that there is no difference between gamma rays and X-rays. The only thing that matters is where they're produced. Gamma rays will come from the nucleus, X-rays will come from changes in the shell configuration. Electron configurations change and they'll emit X-rays. This we talked about a little bit. As one electron moves from a higher orbital to a lower orbital, there will be an X-ray emitted, and that energy is known and can be measured. When dealing with charged particle interactions, right, there are a few things that can happen, right? Ionization, excitation, and Bremsstrahlung. We'll go through each of these quickly. There's a difference between charged particle interactions that are directly ionizing and those that are indirectly ionizing, and it's sort of esoteric and weird. We'll get to that shortly. All right, so the diagram here is illustrating an electron moving in the neighborhood of another atom. All right, so what happens is there is an interaction between the two electrons. Right? And if the energy is sufficient and if the distance is near enough, it can essentially knock off one of these electrons through a coulombic interaction. Right? And that's ionization. Right? Excitation can occur if the distance is greater or if the energy is not so great. The interaction, the collision, I'll speak of loosely, will lead to one of the electrons in the atom going to an excited state, right? So it just bounces up a couple of energy levels. Bremsstrahlung occurs when an electron is moving in the neighborhood of a nucleus, and this is how we produce X-rays. And because the electron has a negative charge and the nucleus has a positive charge, the electron that's passing by the nucleus will be accelerated, and there will be an emission of a photon because of the accelerated electron. It's just changing direction. Charge and motion, right, will lead to magnetic fields, will lead to production of these X-rays. All charged particles will have a range associated with them, right? And it's dependent upon the energy of the particle and the material through which it is moving. Right, so the range of a 1 MeV electron moving in air is going to be different than a 1 MeV electron moving in lead or in chicken feathers or in water, whatever. Photon interactions, they typically will not speak of a range associated with them. Right? It's more a probability of interaction. Again, we talked about before how most alpha particles can be stopped in the dead layer of skin. Right? It's just because they give up their energy very, very quickly. They interact quickly. Right? Linear energy transfer refers to the way that, as it says, the way energy is transferred to the medium through which these particles are moving. Right? And this is something that's useful, and you will use this in coming classes. This table shows different LETs for different particles, for different X-rays. And it's just intended to give you an idea of how they vary with particle energy. Neutrons. I doubt that you guys are going to deal with this very much, but it is an interaction that does occur, particularly in radiation oncology. If you have a very energetic photon moving in the neighborhood of a nucleus, there can be neutron production. It typically doesn't occur below about 12 or 15 MeV, but once you get above that threshold, then there can be neutron production. There are different classifications for neutrons, right? They'll refer to them as slow or thermal or fast, and this is all dependent upon the energy of the neutron. For what we're dealing with, almost all neutrons will begin their lives as fast, right? And then they're moderated or they slow down, right? And then they'll become slow or thermal. And it's because of the way that they interact with the environment. Elastic scattering, this is more like pool balls, billiard balls on a pool table. Energy is conserved again, right? A neutron will bang into a nucleus, right? Or a proton in this example, and it will just, a fraction of the neutron energy, right, will be carried off by the proton, and that's illustrated here. Right, because neutrons and protons are of a similar size, for shielding them, it's typically better to use materials that are similar. So water is a good shielding material, paraffin, different waxes, stuff like that. Anything that has a lot of hydrogen is really good for the shielding of neutrons. Inelastic scattering, I think we have a nice little diagram. No, we don't. Spallation is the example that they use on stuff like this. If, say, a neutron is moving at very high speeds, high energies, it can interact with the nucleus and essentially splatter it out all over the place. So many of the particles will carry away the energy of the incident neutron. That's all we're going to say about that. When dealing with photon interactions, right, there are three major mechanisms that you need to know about, right, and they are the photoelectric effect, Compton scattering, and pair production. The only thing that Einstein won the Nobel Prize for was the photoelectric effect. It's kind of a little-known paper that he published in 1905. It's nice, it's elegant, and the math makes sense. Some of his other stuff wasn't accepted quickly. So there were many skeptics about that for years and years, but the one prize that he won was for this, the photoelectric effect. A photon is incident upon an atom, right? It strikes or interacts with one of the electrons and bangs it out of there completely, right? So typically it's a K-shell electron, but it doesn't have to be, right? And all of the energy of the incident photon is transferred to the electron, right? So it's a nice, elegant little process, not sloppy, right? Right, so all of the energy here is transferred to the electron, right? So the energy that the electron carries off following the interaction is equal to the incident photon's energy minus whatever binding energy there is in the atom that's being impacted. The photoelectric effect, nice. There's a probability associated with it. These things are all pretty well explained. It occurs more frequently, right, with low energy photons and higher Z materials, bone, lead, metals, etc. This is just a spectrum, an idealized spectrum of photon energy and interacting with a specific atom, right? As the energy increases, right, the probability of interaction decreases, right? And we'll get to this shortly. These things conspire, they add together, right? And you can, dependent upon the photon energy, to determine what process is more likely to occur. There are different edges associated with the spectra, right? So this one illustrates the K edge, and it's talking about the insidemost electron, the K shell electron, and its preference, right, to eject electrons that are of specific quantum energies. That's a poor explanation. I'll try again. All right, so when it comes to Compton scattering, this one is a little messier, right? There is a photon that is incident on an atom, right? An interaction occurs with the electron in the orbital, right? The electron is ejected, but the photon is not completely absorbed, it's scattered, so some fraction of the incident photon's energy is taken off by a scattered photon, and some of it is given to the ejected electron, right? And this is more of a scattering sort of arrangement, right? And the energy of the Compton electron can vary, right? And it depends upon the angle through which it is scattered. Right? The incident photon has a specific energy. It bangs into this electron, and depending upon the angle at which it's ejected, the energy that it carries away and the energy that the scattered photon carries away will differ. Right? And this is a nice little diagram of it. Right? And maybe we have the equation for it. Right? So this, you can calculate the scattered energy of the photon if you know the angles that are involved, and you can calculate any one of these things knowing one of the others. Not difficult. Compton scattering. This is one of the things that makes doing spectroscopy difficult, because it's a continuous process, right? And the energies emitted are not specific, right? It tends to complicate measurement of energies of the different photons and electrons involved. Pair production, this too occurs at only higher energies. You need to have at least 1.02 MeV, a photon of that energy moving in the neighborhood of a nucleus for pair production to occur. Right, again, the pair that's being referred to here is an electron and a positron. They'll travel in different directions. With all of these interactions, you have to conserve charge, you have to conserve momentum, you have to conserve energy, right? So they'll typically be moving away from one another. Doesn't occur at all beneath 1 MeV. And as the energy of the photon increases, the likelihood, the probability of pair production increases dramatically. I think we have, where's my diagram? Okay, so the point here is that as photon energy increases, right, the likelihood of pair production occurring increases as well. So at lower energies, right, the likelihood of a photoelectric interaction is high. But with increasing photon energy, Compton will be preferred for a large range of energies, say between 100 keV and about 2 MeV, right? So these are different processes that occur depending upon the incident photon energy, right? And the blue line here, the total interaction, right? That's the one that you want to pay attention to. Excuse me. Again, the thing to remember is that different interactions will occur, and it depends upon the photon energy. With increasing energy, the likelihood of a specific interaction increases. Attenuation, this is something that's pretty straightforward. Something that you have seen before, presumably. It's dealing with shielding for our purposes. Right, you have some incident photon flux, it strikes some absorber, some barrier, right? And through these different interactions, the intensity of the photon flux will be diminished, right? And it can be calculated using this stuff here. The thickness of the material needs to be known, the type of material that you're using, the photon energy needs to be known, and with these things, you can do some nice calculations dealing with attenuation of photons. Blah, blah, blah. All right, so different units of exposure and dose, right? The Röntgen, this isn't something that people use much anymore in the calculation of, say, therapeutic doses. It's a measure of exposure, the ability of photons to produce ionization. It's something that is used by people like me, for example. It's easy to measure, so when you're calibrating instruments to perform these kinds of surveys, right, the Röntgen is a nice unit, right? Most of the survey meters that you see will measure radiation fields in Röntgen per hour, milliröntgen per hour, whatever. It deals only with photon radiations. And it's useful, but for your purposes, it's not something that you're going to deal with very often. Of more interest to you will be the absorbed dose, right? And dose is always dose. It's just energy per mass, right? How much energy is deposited into some volume containing some mass, right? And there are different units that are used for this. Rads and grays are common. The grays are the MKS units, so they're preferred. The older units, rads, these are CGS units, so centimeters, grams, seconds, rather than meters, kilograms, seconds. Right, so the conversion between them is pretty straightforward. For photons in air, they give you the conversion here. 1 Röntgen is equal to about 0.877 rads. It varies for tissue, but again, it's unlikely that you're going to use stuff that involves Röntgen. REM, right, this is a measure of potential biological damage. Depending upon the particles that are involved, right, you have to modify the energy by a quality factor before you can talk about risk associated with exposure to these different types of radiations. What we're concerned with here is biological damage, right? So you convert that by using a quality factor that's associated with the different particles, right, in order to produce what is known as a dose equivalent. Right, so depending upon the scheme that you use, different particles will have different quality factors. The stuff that we use in the US, right, this is a nice example of that, but internationally, because they're regulated differently, because they think about it differently, they'll use different quality factors for the different particles. Again, most of the time for the stuff that you're going to be doing in the clinic, 1 Röntgen is equivalent to 1 rad, which is equivalent to 1 rem. It's useful in the clinic. You're probably familiar with it. Where there are many transistors that we can do that they don't for link or shorter. The problem is once positive electrons is permitted to from this, it will form a neutron interact with it will to these will to the crack and will another frequency. Right. So common there's there are photons that are result of this action or action, right? They go in different directions and then the 5 or 1100 even KV so right, so energetic jet, it's the energetic should full use. The answers that are around the drone very hard on our captain character. What happens here is there are any pro in this and eventually the new will this reads just natural outcomes. One of those these cons to vertical new and holds a to K in the shell. So the program is connected to trying to elect trying to mid K from the ocean. Select the electron so in orbital orbit will fall in lower two-fold laterals and the characteristic that are raised in right transition positions. That's very kind of a good example. Does electric capture on campus at you? Doesn't good example is I will only have 25. Just this bad diagram. Sorry. 21 would be 5 for example. I will down from our any sample examples. Actually, commonly the photon and times energy electron trying to capture going are to be compared to parents believe all. It does occur in a free that it realizes some will use things that not I mean, take a picture. I make often out the particle, out the particle, the school out atom from nucleus, and the nucleus is making channeling, ratting, still choosing jet energy, that it's saying it's size of data. So, it's going to create camera mission, get right, and company, commission, company, out me, mission, there's almost always sort vote of machines and the number of technicians got organized we use recalibration is energy and it's product it's a foot on the top it's cut the boat that are emitted added from the cynically and it's in the so diagrams here's the considerable disparity of the particle natives and side next days and then in order to go to the downwards and ground state about the bits of times photon the things these can happen pretty quickly pretty fractions of action right so just slow and I go back for them again energies you can measure think the measure here is there no desert difference between days more race and the everything there's matter there's one do will raise from complete new excess will raise from ancient changes in the alkylation grades like contributions and grading change in the middle excess this talk we a little about this as one on back test remove iron order to total board with a wicks and emitted and energy with dealing part theoretical action right there think you can't stick have they kind of like an explanation straight around go through to the there's this free different traditional artifact interactions are that like and I think there are those like and I say sort of terrorist we we'll get that to short right so the diagram was resulting in a lot of tripping movie in the name of so what happens is there an interaction between the two electrons and if it entered the G is substitution and it's and it can actually send out what God let these electrons through a normal back that's it case like connection with the current dish is considered great is energy to not great generate the actually option back of solution will lead to one level of the in that of go to bring and added sites to nice so just as now cover up energy events. Rem curling is when electron beings moving in neighborhoods and notably a nucleus is how next uses and this the electron have negative to the charge nucleus as a part of charge the electron and this being has light by new elements will fix and it is will be any of a time vote because of selected just is ancient change direct ocean to feel fields to build up production all chart wills have gained ratios just weighted it's a tendency depending upon the energy cycle particle and built period through web so the gain rate of one LV contact and moving is going to be for one and a windy LV move trying lighting and everything I can be shakers at that rate and water one time photo action interactions they do not we will be of integration so with more it's a bit probability action which give up to more for most alpha chemicals top is to slayer and yeah it can just give us the end of their very G with very very inner quick time any tragic from errors ways to the as the energy transition is used for Williams meet which through parts of the muscles and this is something useful use and use this slamming these are bullshit so different this fresh TLE 40s different particles for the court board and phrase strings so it did 10 give you an idea how of to barely back party with ethical energy neutrons I should out guys know what the deal during this is in the action or reduction that occurs significantly rarely as engaged you have if you have energy and folk talking in move neighbor the neighborhood of new slave standard tree new down prediction it does not occur typically once you get above that then the rabbin can to new and there are classifications of accordance to nutrients for the low, slower, or more or have all the fun and for what period we're dealing with almost all on the trials will be on their sides and factors where in the modern state or they slow down and then become or slow become it's the ways that they act around elastic considering like more cool small from your built all able to build energy and sees curve and again and will and to a neutral split and prototype in this example time section that will and is an action of a new non-trunk energy that will carry big auto to the program and the roaster because new sun pro and runs time or similar of a for still the sheet that it's think better use you to materials that are similar water is going to building material if there different pack and stuff so that like the thing that anything has is hydrogen is real shape for the building any class area gap it's a nice that's no like exists the example is like it's if a new and try to it's putting up very basic heights be energy it can interact energy with this and it actually sends blasts out the rest of the place also part of those like will give the air where energy will the air So let's say we're going to when dealing with deal time photo action interaction, right, there are three major mechanisms to know and they are photo of the electric effect and counter escape herring and the only thing that I one time know about the I power was for was the electric effect and was little the paper nights and it's a man and I know there's was stuff that's next so the raptors got to those 3 years per year. So the guys on where there's one of the like photo of his time to instant upon an incident on Adam and it extract or act or one with the and tons saying that out completely. So it's typically a picture collect electrons and all the energy and the other incident it transferred to his electron. So it's a size against a little bit slats so right so all energy is here as transferred to the electron right so the energy electron area and the power actually is equal to the energy whatever is energy what is there in atoms state this path in the electrical effect what the slide so there's a probability that we'll see the things these are pretty all like well it prefers it prefers free morphly lower with the flange on both types and high shared here image and photos that's let settle just to affect the spectrum just an ideal spectrum of photon energy and interacting as energy the energy increases the energy the ability of interaction act we'll get the shit to the for get things inspired by the and they act and you can depend on it and photon the energy to confirm what this is more like there are edge for stated those which effects it's just one of the straight illustrates the edge not just talk about the signs mode okay the collection and it preps for it right to jet actions that are less specific on quality and very important. Right. Yeah. So, all right, a couple of times to captains of swearing is method there is on the potencies to find on the add and actually interact with his electron in the orbital the electron is ejected but the photon is completely absorbed it's fractions the of the inside time energy just off can buy as I heard the gas out and so it's own for the get to eject each like the so this is more of a string matter or the brain and energy of how the electron and control and depends upon and the triangle which is it gets against the incident photon tosses as the city and hang back to the center like and it's makes upon and that it's just with energy and carry the way is the energy and the energy there forget on what there is the photon and this is a little diagram of it we have the core so this and calculate how I can get the standard of G to the function. If I know if you angle the solution, you all calculate these one thing and one knowing of these. That's not getting some headering. One of this is things that makes things traffic people. It's not difficult. It's continuous in your energy in the emit is not specific. It tends to compensate the measurement of mental energy of difference of time collected prepare an action to stir accumulation that other high energies that need to leave of energy at 1.0.2 VME of that kind of energy entering and move to that the neighborhood new of and discipline pair for extra product into a fitter and pair the different here to is erection of planet process and the level different induction rails and all the all max energy actions when charge serves concern to energy so right typical typically move to wait another one doesn't occur at all. People need one and all, and at the end, the energy flow to the food is basically light profitability of the addiction reduction is just command like breathing from food. Yeah, okay. So, the point here is that says both the energy is light politically preparation of Dr. produces pretty well, just focus on low at energy or energy. Or like a focus left back in our institution with focusing on energy will be bird for a large range of energies of ABGC 120 energy evens and me energy so right so these are processes depending on the instant photon and the blue here I hope that that's the one you want to pay attention to. Excuse me. Again, dream thing is remember that it's different track and intervolations were occurred and it depends on the time with the energy sync the likelihood of against seduction or averages increase the anyway, attend the station. This is something that's pretty forward. You aim for presentably dealing with deal for purposes. You have some incident flood, some right numbers or bear some barrier, and through the different back interaction, the intensity of so the flood on feeds will diminish. You can enjoy using the healthy state here. The stick of the ministerial material needs the tone and the type of material used. Using from the energy and these with things they can do can nice and like how you use on selling the Daniel with the innovation with so right unit for subdurable right the rent this is something that people not use more anymore. You will change more in the calculation of say therapy. Computers, it's a measure of MITS ability of portfolio of folks time used for design some it's the things use like PP for me for example it's measure so how you're getting inbred instrument from the 490s services the right rent and is a nice it's motivate the service meters will measure rent field and rent person or rent miller per hour field it only photo with that rate tension it's useful, but your preferred purposes you're not something something that you're going to deal with. And more citrus be will the stove and right don't always is almost just it's cheap energy map right but your how much energy is to deposit in some volumes of volcanoes consuming and they're different they're this you this for the adds a ray cabin raise gram for the SAS units per if you get the old student these are GSC units here semi centers branch the sound seconds and the cedar grand kiloseconds it's the conversion in between these for time in air give you the converted conversion number one and to zero zoom about open 787 right. Very for case two tissue very 10 gives it like but it is the right is revolving. This is a measure of potential bible jamming depending upon the part of the ripples on right to have modified energy and by default either back or you fly into rip up so it's because it was particular goes to if these type of radiation but we're with here is what you call jamming here which so you can convert that is by equality the faculty for the thing with the part from full cycle right in order to do this also say no so you can so depending on the thing that you different political have different faculty we when the use US this uses ideas that's an international national there does give a deflated as a lot of different different usability qualities factor for the critical particles again the test for the time that you're going and doing one again rent equivalency 1 to rent which is equivalent and sleep most participants so